Well, let's take a look at 1.7 periodic trends. This is one that you should have familiarized yourself before because we've done it before. We're going to take a little deeper. And one of the things that we're going to utilize quite a bit is what's called Coulomb's law. Now, this is Coulomb's law over here. However, there's just really one key component to look over. This is just a constant. Pi is pi. E naught is something else. This is just a constant. But these are two charges and the radius, meaning that there's some energy needed to overcome it. So E is potential energy proportional to force. Often we think of attractive force. Repulsive force is also true, but we often think of attraction more than repulsion in chem. So really what we want to see is that when the charges are the same, energy is positive and gets less when R is larger. So these would be repelling. So as you have two repelling forces further away, you have less potential energy. When the charges are different, energy is negative. It gets larger when the R is smaller. So if you have a positive and a negative, you bring them closer together, the stronger energy is going to occur, which means it's going to be a negative energy. So bigger the charges, the more potential energy. This concept's used explaining what we see with the nucleus and electrons. So this is what you often want to use when we talk about, according to Coulomb's law, this is what is occurring, because this shows you have the idea of these attractive forces to the nucleus and like outer electrons, and then the size that occurs between the two. So how useful is this? Well, the idea of periodic law was used by Dmitry Mendeleev. He predicted properties of lots of elements, all based upon patterns. So his predicted patterns, even some of the most numerical ones, are actually spot on with what was actually there for gallium and germanium. This was well before he did even many measurements in the early 1900s. So this has a really strong usefulness in chemistry because of these repeated patterns. So some summaries of these. We have the radius getting smaller as we go right to left. Ionization energy, electronegativity, electron affinity, and effective nuclear charge all increase going from left to right. The radius of the atom in shielding increases as you go down the periodic table, while ionization energy, electronegativity, and electron affinity increase as you go up. So keep those in mind as you go through and talk about these periodic trends. Another kind of way to look at it, they also talk about metallic character. Those usually deal with the idea of physical properties. Again, non-metallic going up by our nonmetals, more metallic as you go away from the nonmetals. All this kind of coordinates together, but you need to understand these and know the directions of these so you can talk about these and explain why. So here's a little quadrant that kind of gives the ideas of things that are maximum attraction, minimum attraction, and then intermediate. So the distance minimum, that's the atomic radius, so to speak, and then the effective charge. So something like fluorine has the maximum electronegativity, electron affinity, and ionization energy because it has a large effective charge with its number of protons and small distance between those electrons and the nucleus. So that enables all of these to be the highest. Minimum ionic and atomic radius because it's the smallest, and therefore if you give off its outer electrons, it's going to have the smallest ionic radius as well. Over here in the intermediate side is you can have a small effective attraction, but also a small distance. So small nucleus, small distance, and like iodine, large attractive force with its, we got 53 protons, but it's very large. So it has intermediate attractive force to those electrons. Minimum, very small effective charge and very large distance. So something like cesium is huge, where it has a maximum atomic radius, therefore a maximum ionic radius, but minimum ability to attract electrons from another atom, attract electrons to an ion, and give up that ionization energy, give up that electron in order to have a low ionization energy. So minimally attracted valence electrons. So let's get into these different things. Atomic radius, size matters. It's the biggest thing. There's a couple ways to measure. There's the individual atom, which is called the van der Waals radius, or the covalent radius when things are bonded together. They basically take the average of the width and divide it. They're slightly different values, but that's not too relevant to us. The atomic radius is the average radius based on large numbers of elements and compounds. So these will actually change based upon what's bonded to what. So even though you say bromine in bromine is this 114, when it's bonded to hydrogen, it might be a little bit less. So we take kind of an average of all the different representations we're going to see and say that's the atomic radius. So key points to describe. Can't just say because there's more shielding. Again, don't drop that vocab. Size of an atom is related to the distance the electrons are from the nucleus. So that's the way you want to talk about it. The outer electrons, valence electrons, are further from the nucleus, closer to the nucleus. You also must specifically mention that a higher energy level is bigger and further away. I know it seems obvious, but you want to talk about this because the way these are graded are based upon looking at like highlights. So if you miss a highlight because you're not really using the proper vocabulary or explanation, you're going to miss it. So don't be vague, but you don't have to ramble on for on and on. Now remember, this is going down a group. When we think of increases down a group from top to bottom, this increases by adding a principal energy level. Quantum mechanics is something we'll talk about a little bit later, but that goes into the depths of why atoms and things do what they do. Now, when you have a larger principal energy level, a larger energy level, it's larger in volume. That means the electrons are furthest away. And again, when we talk about Coulomb's law, that means that there's going to be less attraction to the nucleus. There's also an addition of more shielding from the valence electrons. So therefore, you get larger radius. Because those outer electrons are less attracted, they're able to swell due to the fact that the inner electrons are shielding, therefore not as attracted. And also, you have a higher energy level, so they're further away. Now we go across the period. Can't just say there's a greater effective nuclear charge. Again, the size of the atoms related to the distance those electrons are from the nucleus. You go to the right, there's more protons, but there's also more shielding. There's more protons, but the shielding doesn't increase because you're not increasing electrons on a lower energy level. They're just on the same energy level. Again, specifically mention that this results in a greater attraction, therefore smaller radius. Always get down to the explanation of the why, not just the description of the how or what. Again, be careful. When we think of quantum mechanics, decreases across the right, you add a proton, and there's no addition to shielding. So when you have that, the effective nuclear charge goes up, stronger the attraction, and again, the stronger the attraction means the higher the smaller the radius, because Coulomb's law is the charges over the radius. The charges aren't changing. You still have the electron and the same nucleus, so those are the same, but you're going to have a stronger attractive force because they got closer together. Therefore, you end up getting a smaller radius. So you want to, when you're talking about explaining this, you're putting this into terms. But again, it's not a paragraph. It's, a few sentences. But saying the right things is critical to showing that you understand what we're talking about. All right, well, let's look at our next trend, ionic radius. Ions in the same group have the same charge. So all things in group 1 have a positive 1 charge, positive 2 charge for group 2. Now you go over group 17, they have a 1 minus charge. Remember what happens to your positive and your negative ions when we have electrons gained or lost. So simply put, ionic size increases down a column, higher valence shell, it's just going to have one more energy level. So the same reason applies when we talk about atomic radius. Now, cations are always smaller than the neutral, anions are bigger, therefore cations are always smaller than anions in the same energy level or of the same atom, although atoms generally don't make cations and anions. Now, the larger the positive charge, the smaller the cation for things that have just one isoelectron, same configuration. So when we think of what's down below, These all have 1s2, 2s2, 2p6 as their electron configuration. But magnesium is going to have the smallest size because it has more protons. It's pulling those electrons in, higher effective nuclear charge, therefore shrinking those down, while something like oxygen, gaining 2 electrons to get the 2p6, is going to be quite large in comparison because it has 4 less protons. To put this visually, you got the neutral, the cation, and the anion, so you can see all of these make positive 1s. Don't worry about the values as far as what they have there, but you can see as you go down, just like the atoms get bigger, so do the ions because they still have 1 more energy level here than they do here. On the otherwise, the anions are going to swell due to the fact that they're gaining electrons. Those electrons are going to repel against each other and push out due to also the fact you have the same shielding going on and less protons than you do here than you do here. So you can see that fluorine's got 1 more proton, so it makes it slightly tighter. That doesn't always hold up when you start getting into the different energy levels, but the idea is that the anions are always going to be larger than the other ones. So ionization energy, our next one. So this is our energy, minimum energy to remove an electron. That's key, remove an electron from an atom or one that's already lost one and it's now an ion. This is talked about in the gas state. That's just because you can have individual ions and nothing's bonded to each other. It's going to take energy. It's endothermic. You have to add energy in to remove the electron. This overcomes the coulombic attraction. Valence electron, easiest to remove, lowest electron ionization energy, because again, it's shielded, has less attraction, therefore less energy needed. So for example, if you have this random thing as a gas, plus you add the energy, you get an ion and an electron. Where's that electron go? It might go to another atom. It might go as electrical charge going out throughout space. If you want to do it again, you're going to have a second ionization energy. So that's how you go from M1 to M2, or I should say 1 plus to 2 plus. This increases across the period, left to right. Each time you go, you're adding a proton. Got that. No increase in shielding because the same energy level. They don't always do the same at inner levels. Increasing nuclear attraction. You're decreasing in repulsion since there's 1 less electron. So harder to take 1 away, or more than 1 away, because you've increased electrons. So if you got 2 electrons out here and you remove 1, it's gone, then the remaining electron is going to be able to get closer, which means the subsequent energy, the subsequent ionization energy is going to be higher. Now this decreases down a group. Each time you go, you got another energy level, means that you have more core electron shielding. Further away, this has a decreased nuclear attraction, easier to take away 1 electron, therefore a decreased ionization energy. Now you do get some irregularities, always going to be the case. Half-filled or totally filled sublevels. You get extra repulsions and paired orbitals. Those are the ones that have going up and down. Makes it easier to remove an electron, lower ionization energy expected. So when you have half-filled or totally filled, it's going to be easier to do. When you're moving to a p orbital, the p orbital, remember, doesn't penetrate as much as the s orbital. Less nuclear attraction, lower ionization energy than expected. You'd expect it to be kind of another notch over, but it's going to be slightly less because there is no penetration by those p orbitals, just the s ones. So you can kind of see these different ionization energies, these first ones. So when you go from lithium down at the lowest, then you have, what's over next? Beryllium. You're going to have these increases and decreases. So when you see when there's these dips, these are when the energy levels are kind of half filled or filled. So that's where it kind of dips down. This is the P. This is when it's half filled. That's the rest of the P. Again, same dip here, P. You see this kind of here. We come across the transition elements. Those are going to be different for a variety of reasons. And again, you kind of see they more transition out or become more linear as you go further away because there's less variation with less of the shielding going on. So you see these trends. decreasing generally as you come across. But of course, as you go from something like here to sodium, there's a dip and then general increase. When you think of things being half filled, there's a general decrease slightly, but these become a little less irregular. We're looking more for the idea of increasing across, decreasing coming down. That's going to be what your main focus will be. Now, if you take away more than one electron, it's going to take more and more ionization energy. Each time you take one away, the atom, I should say the ion, now that remains, gets smaller. Smaller atom, closer nuclear attraction, meaning higher coulombic attraction. Harder to take another one away, you need more ionization energy. So sodium, which only has one valence electron, you got this here. To take away another electron, now that's going to be an inner electron, not a valence. This is going to be your 2p6. And you can see that it's so much closer, and it also is going to experience a higher attractive force. You're going to experience a huge jump because of the fact that coulombic attraction is the charge over R. And because it's over R, the fact that that's over R, it makes a bigger jump when the radius changes. Magnesium with its 2 valence electrons, you say, okay, gets up pretty good. Going another one, because it got smaller, go to another energy level, huge. So this can be another way of identifying, hey, this must have had 3 valence electrons because the dramatic jump in energy for the ionization energy got that much larger. So that means you're removing core electrons. Helps you figure out the charge on the element or what element it might be, because they always love on the AP test having you examine information and identify what element is this, what compound is this, and so on. So you can see that as you go, aluminum's got 3+, silicon's got 4 electrons, phosphorus has 5, and you can see how this goes down to where even when you get to 7, of how big, yes, it's increased, but we haven't started removing core electrons. We've just removed the valence. All right, now we come to the least favorite one that I am of, and I think most chemists are, and it's electron affinity. It's just not one that's used that much, not only to explain how things work, but also everything else. Ionization energy, electronegativity, atomic radius, those are like the 3 top ones. Ionic radius probably right behind it. And then you've got electron affinity. But let's go through it because they could come up, and hopefully we can get it right. So this is the change in energy when a neutral atom gains an electron. So it's almost like becoming a negative ion, because ionization energy is all about becoming positive ions. It's usually energy is released. Usually, is again why we don't like it that much, which means it's exothermic, it's going to be a negative value. Some alkali metals and all noble gases are endothermic, because alkali metals aren't going to want to take on an electron, so you're going to need to add that together. But we generally don't talk about electron affinity when we talk about metals. We talk about the nonmetals. More energy released, the larger the electron affinity. So the larger negative number, the larger electron affinity. Sometimes students get that mixed up. So alkali metals decrease down the column, but not all groups do. So sometimes it might be the same. It's really irregular from the second period to the third period, probably because there's that transitional D energy level that can be kind of bounced around from time to time. It generally increases across a period, becomes more negative from left to right, not always absolute. Electron must pair here. So these exceptions, I don't think you really should focus too much on. The idea is more of the idea of getting the generally idea. So see, decrease as you go down, but not all groups do. And again, generally increases across the period. Highest electron affinity is going to be your halogens. Okay. This is, again, another reason why I think teachers and people don't like using electron affinity, because of its irregularities. So here's just the values at hand. You can see generally is decreasing, down, not so much, decreasing, increasing. See how varied it gets down here? It doesn't seem to work much for this across, but going across it seems to get larger with a dip in here as your middle range gets filled in, kind of like what we were talking about where the atoms are and their ability to attract. So again, really tough one to talk about, but let's try to get there. So again, another example that you have the amounts going through. You can see there's a general pattern. It picks up, dips down, picks up as you go to the next energy level, starting off with your, your 1s2. This is your beginning of 2, beginning of 3, beginning of 4 energy levels. So not too much to focus on that one there. Electronegativity. This one's used a lot with bonding, so this is one's definitely we want to hit on very hard. So this is the ability to attract electrons to itself. So pulling one electron away from it so it has it more around itself. We talk about with bonding and different types of what are called sigma and pi bonds. Now, this increases across the period. You go left to right, decreases down. Fluorine's the most, francium's the least. We don't talk about noble gas atoms. They do bond, but not in this general sense. They do some other more tricky stuff that we won't really get too deep into. This is the opposite of the atomic size trend. The smaller you are, generally is going to be the more highly electronegative you are. When we have a difference in electronegativity between the two, you're going to have more polar bonds. Negative end is going to be more towards the electronegative atom. We'll get to that later when we talk about bonding. So this one, again, is much more regular, with the exception of hydrogen, because it's just so weird. You can see that the alkaline metals will decreasing. We stick with generally the S and P blocks when we talk about our trends. You can see definite increase across here. And of course, decreasing as we come down. This looks like it's actually increasing here. If you're needing to determine these, you'll be given the values to these. These aren't something you're going to memorize. You want to memorize and kind of understand the trends. Again, the periodic table, the AP test is not really big on memorization. They want you to understand a tendency or a trend and then be able to explain that trend. So that's what we're doing more likely here. All right, I think that's the end of our periodic trends. Get some practice in using them, ask me some questions about them. We can look at some of the exceptions, but we're going to mostly want to focus on the general rules of what we see as the trends for these in our explanations. And remember, always focus on the idea of Coulomb's law, size, attraction, talk about shielding, and talk about why there are some of the exceptions and why this actually works the way it does. Take care, and I'll talk to you later. Let me know what questions you got.